So what about the deadlock prevention? So prevention is a kind of a scheme in which the system is being designed in such a way so that deadlock, the situation of deadlock doesn't arise. It means it becomes impossible to have the deadlock. Now, as far as the prevention is concerned, it is different from the avoidance as well as the detection, because in this particular case, we are not going to test a runtime about the allocation, whatever is need to be performed. Now we have already seen that we have 4 conditions for which has to occur simultaneously for a deadlock. That is mutual exclusion, hold and wait, no preemption, and circular wait. These are the 4 necessary conditions for a deadlock to occur in a particular system. So we can somehow able to ensure that at least one of these conditions is never satisfied. Then only the deadlock will be impossible. So with this particular idea, we have 3 important deadlock prevention methods. These methods are collective request is the first one, ordered request, and the preemption. This collective request, it is going to deny hold and wait condition. The ordered request is going to deny the circular wait, and preemption is going to deny the no preemption. So we are left with only one, which is the mutual exclusion. So as far as the mutual exclusion condition is concerned, it can also be denied by for some non-shareable resources by adopting some alternative methods of using those resources. And how it can be done? Let us take an example of a printer. Printer is a non-shareable resource. So the technique which we can apply about denying the mutual exclusion condition with this non-shareable resource, that is printer, can be done. It can be done with the help of spooling the printer output. Now, several processes can generate output at the same time. They are spooled, and this spooled output are transferred one by one to the printer. So therefore, this alternative way of using the printer, it can be applied only for the printer also. It cannot be applied for the other resources also. So this alternative way of printer is the only process that actually requests for the physical printer. It means we have to devise a certain way by which we can request to the physical printer. So this particular way cannot be made as in the form of a request for the other resources also. So as far as the deadlock of the printer is concerned, it can be impossible if we adopt this particular method. This is called the spooling. But in general, it is not possible to prevent the deadlock by denying the mutual exclusion condition, because we have some resources which are internally non-shareable, and it is not possible to devise an alternative way of using them. So the denial of the mutual exclusion condition for the deadlock prevention is rarely used. So we have other methods also, and those methods, as it has been mentioned, let us discuss one by one. The first one is the collective request. So as it is stated earlier also, that it is going to deny the hold and wait condition. And how it is being done? It is done by ensuring that whatever a process requests a resource, it does not hold any other resources. So we have certain policies for the allocation of the resources, and there are 2 policies. The first policy is that a process must request all of its resources before it begins its execution. So if all the needed resources are available, then they are allocated to the process, so that process can make the execution for its for its completion of the job. But if one or more of the requested resources are not available, which is requested by the process, none will be allotted to the process, and process have to wait. So this is about the first strategy. The second one is, instead of requesting all its resources before the execution starts, a process may request resources during the execution if it follows certain rules. And that is, if it requests the resources only when it holds no other resources. If it doesn't hold any kind of resources, then only it can request the resource. So if the process which is holding some of the resources, it can adhere to this rule, and by first releasing all of them and then re-requesting all the necessary resources. Meaning thereby, the first scheme is that all resources has to be requested in the beginning. In the second, it can request while doing the execution, but the condition is it does not hold any resource. But if it is holding some of the resources and then it is requesting other resources, then first it has to release all of these resources and then have to re-request all the necessary resources, whatever is required. So as far as these two policies are concerned, second policy is preferred over the first policy, because second policy is having certain kind of the advantage. And the advantage is that in the beginning, if we are applying the first strategy, first policy, it may be possible that in the beginning, the process may not be knowing that how many resources will be required and what will be those resources. It may be possible. And in the first condition, the second point is that if it holds all the process, if the processes holds all the resources which it is required, then it unnecessarily will be holding for a very long time, because until unless it is not going to finish its execution, it is not going to release those resources. So it is going to unnecessarily hold the resources for the entire duration of its execution. So that is why the second is being preferred over the first strategy. Now, this collective request method of deadlock prevention it seems to be very simple, and it seems to be effective also, but it has a certain problem. There we have two drawbacks of this scheme. The first is it generally has low resource utilization, because a process may hold many of the resources but may not be actually use several of them for the long time. So meaning thereby, if the resources are being allocated to the particular process, whenever it is being used, it should release it so that other processes can use it. So that is why the meaning of low resource utilization. The second one is it may cause starvation. It may cause starvation about the process, of a process that needs many resources. If a process needs many resources, and so what happens that the process which needs many resources, and whenever it makes a request for the needed resources, one or more of the resources may not be available. So in this case, it may cause starvation. Now the second second method is collective request method. Now this method is going to deny the circular wait. Now in this method, each resource type is assigned a unique global number to impose a total ordering of all the resources. Jitne bhi resources hain, every resources are being numbered with the unique global number. That number is called unique global number. Now, the policy has been framed in such a manner to use those resources according to the process in which the process is going to request at any time. At any time, process can request any kind of the resources. But the process should not request a resource with a number lower than the number of any of the resources which is already holding it. Meaning thereby, if the resource which is held by a particular process is numbered as 3, and it is asking another resource which are having the unique global number, that is 5, then it's okay. But if it is holding 5 number of the resources, fifth number of the resources and it is asking for the third, then it is not possible. It will not be so. So if it is the process, whenever it needs, it requests for the resource, but whatever resource it is asking for getting the permission for the its allocation to that particular process, always it is to be remembered that the number of unique number, that is global number of that resource, must be greater than the resources which is already holding it. So I can take an example that suppose a process holds a resource which is represented by I, and the process may request another resource which is numbered as J. And if J is greater than I, then it's all right. Otherwise, if J is less than I, then it will not be allocated. One more thing is there that if the process needs several units of the same resource, only single request is required for all the units of that particular resource. And uh, this order request has proved that if we follow this particular rule, then the resource allocation graph, and we make a resource allocation graph that will never make a cycle denying all the circular weight condition, and hence the deadlock will become impossible. Now, if I have already given an example that if the particular resource is which is stored, which is held by a particular process is numbered 3, and it is asking for a resource which is having number 7, then the 7 resource, and if it is available, 7 will be granted. But if it is holding 3 and it is asking for it is holding 7 and it is asking for 3, then what it has to do, it is allowed to have the resource number 3, but first of all what you have to, he has to release all the resources whatever it has hold. So this is the possibility by which this ordered request can work. Now the ordering of the resources, how to do this ordering of the resources, it is decided according to the natural uses of the pattern of the resources. Now, if you take an example of two kinds of the resources, suppose the resources tape drive and the printer. So the natural ordering will be, because tape drive is required first, then the printer will be required. So of course, the number of the tape drive will be smaller than the global number of the printer. So this is called the natural ordering. However, this natural ordering depends upon the different types of the job which is being executed in that particular system. So it has to be decided. The ordering of the numbering must be decided before before the execution starts, before the request is to be asked by the different processes. Now, the third one is preemption. Now, this preemption, it is going to deny the no preemption and the resource allocation policy. There are two resource allocation policies, but let us know what is the preemptible resource. A preemptible resource is one whose state can be easily saved and it can be restored later. If you want to take an example of that, the CPU registers and the main memory are one of the very good example of the preemptible resources. So if the resources are preemptible, the deadlocks can be prevented by using either of these two policies. Out of this, the first policy is when a process requests for a resource and that is not currently available, that is not available currently, all the resources held by the process are taken away. That is preempted. All the processes are taken away from it and process is blocked. Now, process is unblocked when the resource requested by it and the source and the resources preempted from it becomes available and can be allocated to it. This is the first policy, that whatever request it has made for the different resources, if it is available, then it will be granted. If it is not available, then it will be blocked, and it will be unblocked when all the resources which it has requested are available, and if it is available, it can be allocated to that process. The second policy is When a process is going to request a resource that is not currently available, the system checks uh, if the requested resource is currently held by a process that is blocked and waiting for some other resources. If it is so, the requested resource is taken away, that is preempted, from the waiting process and given to the requesting process. Otherwise, the requesting process is blocked and waits for the requested resource to become available. So this is the second policy. So in general, the applicability of this particular method for the deadlock prevention is, however, it is extremely limited because it works only for the preempted, uh, preemptable resources. However, the availability of the atomic transaction as well as the global timestamps makes this particular method very attractive uh, as far as the deadlock prevention in the distributed system is concerned. Now, the transaction mechanism, which you have already studied in the operating system, this transaction mechanism is going to allow a transaction, that is the process, to be aborted, that is killed, without any ill effect. And this makes it possible to preempt the resources from the process, holding them without any harm. So in this, in the transaction-based deadlock prevention method, each transaction is assigned a unique priority number by a system. And when two or more transactions are going to compete for the same resources, their priority number are used to break the, the competition. And that for that particular purpose, Lamport's algorithm can be used to generate the system-wide global unique timestamp, and each transaction may be assigned a unique timestamp whenever it is going to be created. Now, uh, this transaction's timestamp may serve as the priority number, uh, and the transaction which is having lower value of the timestamp may have higher priority because it is the older one. So we have two proposals for the deadlock prevention scheme based on the idea which I have just mentioned. The first scheme is the wait die scheme, and second scheme is the wait wound scheme. So what is wait die scheme? In this particular scheme, if a transaction Ti, suppose we have two transactions Ti and Tj. So if a transaction Ti requests for a resource that is currently being held by another transaction, that is Tj. So Ti is blocked. Whenever I say blocked, it means it will be in the wait state. It will be blocked or it will be in the wait state if its timestamp is lower than the Tj. If Ti is lower than Tj, it will be in the wait condition. Otherwise, it is going to be aborted or it is going to die. So we can take an example for the explanation of this, that suppose we have three transactions, T1, T2, and T3. And if T1 is the oldest with the lowest timestamp, and T3 is the youngest with the highest timestamp. Now, if T1 is going to request a resource that is currently held by T2, so T1 will be blocked, will be in the wait state because the timestamp is less, and will be in the wait until the resource is voluntarily released by the transaction T2. Otherwise, on the other hand, if T3 is going to request a resource which is held by T2, T3 will be aborted. So what is the general conception is concerned in the wait die scheme? Whatever is the younger transaction, it is being aborted whenever it is going to request for the resources which is held by an older transaction. So this aborted transaction will be restarted after a predetermined time and will be aborted again if the older transaction is still holding the same resources. So this cycle may be repeated several times before the younger transaction actually gets the resources. So we have a certain disadvantage or drawback of this scheme, and the problem related to wait die scheme is will be discussed. I will be discussing it later on. That uh, the the problem is can be solved by using implementation scheme that ensures that an aborted transaction is restarted only when it is if the requested resources are become available. So that is about the wait die scheme. Let us discuss about the wait wound scheme. In this particular scheme, again, we are taking the TI as the timestamp, which is the uh, timestamp of the request from the resource for the particular resource currently held by another transaction, that is TJ. So TI is going to blocked or will be in the wait state if its timestamp is larger than TJ. In this case, it was smaller than or lower than. In this case, it is larger than T. So it will be in the wait state if the timestamp is larger than TJ. Otherwise, it is aborted. Whenever we talk about aborted, it means it is going to be wounded by the team. So once again, if you take an example of the same, that is T1, T2, T3 are the three transactions. If T1 is going to request a resource which is held by T2, and the resource will be preempted by aborting T2 and will be given to the T1 because of the second situation in which timestamp is larger. Otherwise, if T3 is requesting for the resource which is held by T2, so T3 will be blocked and will have to wait until the resource is going to be voluntarily released, released by the transaction T2. So the wait wound scheme suggests that when a younger transaction is being aborted or wounded by an older transaction, it will be restarted after a predetermined time. And this time it will be blocked and will be in the wait state if its preempted resource is being held by the older transaction. So therefore, the implementation of this wait wound scheme is simpler than the wait die scheme. Now, both this scheme favors the older transactions, which is justified also because in general, the older transaction has run for a longer period of time and has used more system resources than the younger transaction. Now, the deadlock detection. Now, as far as the deadlock detection is concerned, in this particular approach, deadlock detection approach, the system does not make any attempt to prevent the deadlock. It allows the process to make their request for the resources, wait for each other, and the request and the allocation of the resources and the waiting process, all things are done in an uncontrolled manner. So instead, it uses any kind of algorithm which is used for the prevention or it is used for the avoidance, but uses an algorithm that keeps examining the state of the system to determine whether the deadlock has occurred or not. And when the deadlock is occurred, it will be detected by the system and certain action will be taken to recover that particular deadlock. So we have certain methods by which the detection of the deadlock can be done in the distributed system. And uh, the different way, all the way by which it can be detected and try to recover the deadlock situation, uh, it will be using certain process. And the general way of using the deadlock detection process, as far as the centralized system is concerned or the distributed system is concerned, in principle, the algorithm is little bit same, because it is based on the maintenance of the information on the resource allocation to the various processes in the form of a resource allocation graph. And once the resource allocation graph is being made, then try to search whether there is a cycle or whether there is a knot, so in that particular graph or not. So if there is a cycle or a knot in that particular graph, uh, then the system will be in the deadlock state, or it may not be in the deadlock state. So what are the different steps? All the schemes are based on maintaining the wait for the graph and looking for the cycles. And the steps involved are very simple. That first of all, it suggests that construct a separate WFG, that is wait for the graph, for each site. We have many sites and each site will be maintaining its own wait for the graph. And this wait for the graph can be constructed only by the construction of the resource allocation graph. So whatever are the resources which are available at the different particular sites, we first draw the resource allocation graph and then try to find out the wait for the graph for the individual sites for all the resources which are available locally or uh, away from the local site. The second step is convert that resource allocation graph to a corresponding wait for the graph for the individual sites. And once it has been made, we have to take the union of all the wait for the graph for all the sites, and we are going to construct a global wait for the graph. And then we are able to find that if there is a cycle or not. It may be possible that the wait for the graph which is constructed of the individual site, it may contain a cycle. It may be possible that whenever we are taking union of the wait for the graph of all the sites and constructing a global wait for the graph, it may contain a cycle, and then we will try to adopt certain process, certain procedure just to uh, uh, just to detect the deadlock.